We're now going to review the concepts of conditional expectation and conditional variances. We'll see the conditional expectation identity as well as the conditional variance identity, and we'll see an example where we put them to work. This material is useful because we will use it later in the course when we discuss credit derivatives. Let x and y be two random variables. Then the conditional expectation identity states that the expected value of x can be calculated as follows. We first compute the expected value of x conditional on y, and then we actually compute the expected value of that quantity. Likewise, the conditional variance identity states that we can compute the variance of x as the summation of two quantities. First of all, we can compute the expected value of x given y, and then compute the variance of this quantity, and then also compute the variance of the compute the variance of x given y, and compute the expected value of this quantity. Okay? One thing I want to emphasize here is that the expected value of x given y and the variance of x given y are both functions of y and are therefore random variables themselves. So for example, I actually could write this as g of y, say. So this is also a g of y, and maybe the variance of x given y I could write as h of y. So g of y and h of y are random variables. So in fact, I can write the expected value of x as being the expected value of g of y. Okay, and I can write the variance of x as then being equal to the variance of the random variable g of y plus the expected value of the random variable h of y. Okay, so they're the conditional expectation and conditional variance identities, and they can be very useful in many applications. So we'll see one application here. So we want to compute a random sum of random variables. In particular, we're going to let w be equal to x1 plus x2 and so on up to xn, where the xi's are iid with mean mu x and variance sigma x squared, but where n is also a random variable, and this random variable is assumed to be independent of the xi's. So the question that arises is the following. What is the expected value of w? Well, I can compute the expected value of w using the conditional expectation identity. In particular, the expected value of w, well, over here I can write it as being equal to the expected value of w given n. And this quantity here, inside here, is w. Okay. So the expected value of w given n, if you think about it, the expected value of w given n is equal to the expected value of this summation, I equals 1 to n of the xi's. And because n is a constant given n, I should have an n here. Okay, this is equal to the sum n, I equals 1, of the expected value of the xi's, and this is equal to, well, this is equal to mu x, and there's n terms, so that's n mu x. And that's where this comes from here. Okay, so now the mu x is a constant. We can take it outside the outer expectation over here, and we're left with the expected value of n. So that's how we compute the expected value of w. How about the variance of w? Well, we can compute the variance of w by using the conditional variance identity. So this is the conditional variance identity here. We've already calculated the expected value of w given n. It's equal to n times mu x, so that's what this quantity is down here. The variance of w given n, well, that's the variance of this quantity given n. These are n iid random variables, and the variance of n iid random variables is simply n times the variance of one of them, which is sigma x squared. And so we get n times sigma x squared here. So now, the variance of mu x times n, well, mu x is a constant, so it comes out the variance, outside the variance as a square, and we're left with mu x squared times the variance of n. And over here, sigma x squared is a constant, and it comes outside the expectation, and we're left with the expected value of n. So that's how we compute the variance of w. So here's an example with chickens and eggs. A hen lays n eggs, where n is Poisson with parameter lambda, each egg hatches and yields a chicken with probability p, independently of the other eggs and n. Let k be the number of chickens. So the first question I want to ask is, what is the expected value of k given n? And of course, one of the reasons I want to ask this question is because I want to introduce indicator functions, which are often very useful in probability, and in fact we'll use them later in the course. We'll be using indicator functions later in the course to describe the event of companies defaulting on their bonds. So we'll use it to compute the expected number of defaults in a basket of bonds, for example. So it's a good place right now, a good idea right now, to introduce these indicator functions. So what we're going to do is we're going to write the total number of chickens, k, as being the sum from I equals 1 to capital N times 1 subscript hi, where hi is the event that the ith egg hatches. Okay. So in particular, 1 subscript hi, this is the indicator function, and it takes on two possible values. It takes on the value 1 if the ith egg hatches, and it takes on the value 0 otherwise. So in fact, that's an indicator function in general. It takes on two values, 1 and 0. 1 if the event in question occurs, 0 otherwise. In this particular example, the event in question is hi, which is the event that the ith egg hatches. Okay, so we've written k as the sum from I equals 1 to n of these indicator functions. It's also clear that the expected value of one of these indicator functions is easily computed. In particular, it takes on the value 1 with probability p. It takes on the value 0 with probability 1 minus p. And so this is equal to p. So the expected value of the indicator function 1hi is equal to p. So now the expected value of k given n is the expected value of this quantity, which is k given n. And n is a constant at this point because we've conditioned on its value, so we can just take the expectation inside the summation and get this. But we know the expected value of 1hi is equal to p. There's n of these terms, so we get np. So therefore, the expected value of k given n equals n times p, which of course is what you would expect. If you've got n eggs and each of them occurs with probability p, you would expect the total number of chickens to be n times p. Okay, so now we can use the conditional expectation formula to compute the expected value of k. The expected value of k is equal to the expected value of k given n, but that we have calculated there, it's np. So now the expected value of k is the expected value of np. P is a constant, so it can come outside over here. And the expected value of n, well, n is Poisson, we're told, and if we recall, the expected value of a Poisson random variable is equal to lambda, and so that's why we get the lambda down here. And so we see that the expected number of chickens is equal to lambda times p.